Hi everyone, my name is Mason Scher. I'm a senior chemistry major at Drew, and for the last 2 summers I've been working on this project at the Smithsonian, carbon isotope discrimination in ginkgo, testing a paleo CO2 proxy. To break this down a little bit, I've been measuring the carbon isotopic composition of ginkgo growing under a range of carbon dioxide conditions in the hopes that we can use this information to use fossil ginkgo plants and understand the CO2 level under which they grew millions of years ago. So this is something that you're all probably pretty familiar with. CO2 levels are increasing in blue and temperature with it in red. In order to predict how temperature, sea level, and other environmental variables will change with anthropogenic CO2 emissions, scientists use both climate models and information stored in the geologic record. Here we'll be talking about the latter, and also about finding new ways that we can extract information from the geologic record that tells us about past climates, a paleoclimate proxy. We need paleoclimate proxies to understand how Earth systems react to carbon dioxide levels higher than any time in recorded history, and what happens over longer time periods than any in recorded history. So CO2 reconstructions in the distant past are unfortunately very poorly constrained, and we need more proxy methods to refine estimates. A period of particular interest is the Paleocene-Eocene thermal maximum, which occurred about 56 million years ago. With an influx of carbon, temperatures rose globally between 5 to 8 degrees Celsius over a very short period of about 20,000 years. This is the closest analog that we have to our current and projected climate change, so having a good understanding of this period will tell us where we're heading. Now, unfortunately, as you can see from this plot, where each dot represents a paleoclimate CO2 reconstruction, there are very few reconstructions during the Paleocene-Eocene thermal maximum. In order to fill in these gaps and also lead to greater comparison and accuracy between these paleoclimate proxies, we need more methods of reconstructing CO2 levels. So this is where ginkgo comes in. Ginkgo has been around for 270 million years, and it's really excellently preserved. So on the left, you can see that Ginkgo biloba, a modern specimen, is on top of a fossil of Ginkgo wyominghensis, which is extinct, but it looks very similar to Ginkgo biloba. And this is the species that was alive during the Paleocene-Eocene thermal maximum. Now you can see on the right too that ginkgo is exceptionally well preserved. So not only do you have the leaf imprint that's preserved, but you also have the actual leaf tissue that you can then do chemical analyses on and measure the carbon isotopic composition. So we've been growing these ginkgo trees in experimental CO2 chambers for the last 3 years. So these chambers are open topped and they have some environmental variability, but we pump CO2 in. So there are chambers at 400, which is ambient, parts per million carbon dioxide, 600, 800, and 1,000. And there are 3 trees at each level. So for the past few years, I've been taking leaf samples through the summer and analyzing them for their carbon isotopic composition. I do the same with the air samples from around the trees. The idea here is that during photosynthesis, leaves fractionate against isotopically heavy atmospheric 13 CO2, the heavier isotope of carbon. So this all comes down to a kinetic isotope effect that occurs during photosynthesis. So when there are low CO2 conditions, like pictured here on the left, the leaf isn't taking in as much carbon dioxide. So it's not discriminating against the heavy carbon dioxide as much. So we call this a low discrimination, or a low difference in the air composition of carbon and the leaf composition. Now, under higher CO2 conditions, like you can see on the right, there's a larger discrimination and difference between the leaf value and the air value of the carbon isotopic composition. Leaves are able to preferentially incorporate more of the carbon-12 over carbon-13. So we expect to see an increase in discrimination with an increase in CO2 level. Now, this is not what we found in my work over the past 2 summers. So in orange, this is what we expected to see, an increase in carbon isotopic discrimination with an increase in CO2. From my plot, you can see that there's a lot of variability, but we're definitely not seeing a positive relationship between the 2 variables. What we are pretty much seeing is a decrease in discrimination from 400 parts per million trees to 600, and then some variability afterwards. And it turns out that a lot of other researchers working with other species are also seeing a variety of responses. So we see both positive sensitivity values, which is the derivative of discrimination versus CO2. So positive sensitivity is the expected relationship, negative sensitivity is the unexpected, which is what we found. Variety of responses, this does not look good for a paleo CO2 proxy. So some takeaways: we can't anticipate the future without reflecting on the past with paleoclimates. We need more CO2 proxies to refine estimates of CO2 during the Paleocene-Eocene thermal maximum and understand the future. Discrimination in ginkgo and other plants as a paleo-CO2 proxy does not seem to be viable. So thank you very much, and I'm happy to go live to take some questions.